Alright, so let's wrap up this section by definition. So suppose lambda is an eigenvalue of the matrix A, then the eigenspace associated with lambda. The book doesn't have a notation, but many other books use this notation E sub lambda is the null space of A minus lambda I, which is a matrix. In other words, this is the solution space of A minus lambda I times V equal to 0. Alright, so let's do an example with this new definition. So let's consider the 3 by 3 matrix 4, negative 2, 1, 2, 0, 1, 2, negative 2, 3. First step, we solve for eigenvalues. So let's solve the characteristic equation, the determinant of A minus lambda I, A minus lambda I equal to 0. So we get determinant 4 minus lambda, negative 2, 1, 2, negative lambda, 1, 2, negative 2, 3 minus lambda equal to 0. Let's quickly expand this. So it's a 3 by 3 matrix, so the determinant has 6 terms. Let's do the 3 plus positive terms, top left to bottom right. So it's 4 minus lambda times negative lambda times 3 minus lambda. And other two subdiagonals gives you negative 4 and negative 4. So those are the 3 plus terms, and there are 3 minus terms. So the top right to bottom left gives you plus 2 lambda. These 3 gives you plus 2 times 4 minus lambda. And the last 3 gives you plus 4 times 3 minus lambda. I'm not going to spend time expanding these and simplifying them. So this is equal to negative lambda cubed plus 7 lambda squared minus 16 lambda plus 12. And in section 5.3, we learned how to guess roots and factor polynomials. So we're not going to go over that again here. You can check out the videos in section 5.3. So this factors into negative lambda minus 2 squared times lambda minus 3. So we have two eigenvalues, lambda equal to 2 and lambda equal to 3. Two distinct eigenvalues. Alright, so for each of the eigenvalues, we need to solve for the eigenspace. So that's the second step. So let's do it for lambda equal to 2 first. So let's calculate A minus lambda I. This is equal to 4 minus 2, negative 2, 1, 2, 0 minus 2, 1, 2, negative 2, 3 minus 2. So what we get is a matrix with all 3 rows being the same, and we can solve this equation. Well, the 3 rows are identical, so that means the second row and the third row don't tell you anything. We have 1 row, so we have 2 free variables. So y is equal to t and z is equal to s. Then this means x is t minus 1/2 s. So the solution is xyz equals to t minus 1/2 s ts. So it's 110 times t plus negative 1/2 0 1 s. So the eigenspace corresponding to the eigenvalue 2 e sub 2 is equal to the span of these two vectors. So it'll be span of these two vectors here. So it'll be a span of 1 1 0 and negative 1/2 0 1. Now let's do it for the other eigenvalue. So for lambda equals to 3, A minus lambda I is 4 minus 3, negative 2, 1, 2, 0 minus 3, 1, 2, negative 2, 3 minus 3. So it's 1, negative 2, 1, 2, negative 3, 1, 2, negative 2, 0. So let's solve this thing. Oh, forgot a 0 on the right hand side. Negative 2r1 plus r2, negative 2r1 plus r3, 1, negative 2, 1, 0, 0, 0, 0, 1, negative 1, 0, 2, negative 2. It's clear that the third row is twice the second row, so that row does not count. Now we have 3 variables, but one row does not count, so we have one free variable. So if z is equal to t, then y, according to the second row, is also equal to t, and x, according to the first row, is equal to 2y minus z, which is also t. So the solution is xyz equals to t, means 1, 1, 1 times t. So the eigenspace corresponding to the eigenvalue 3 is equal to the span of the vector 1, 1, 1. So in summary, we have two eigenvalues, lambda equal to 2 and lambda equal to 3. For the eigenvalue lambda equal to 2, we have an eigenspace spanned by 2 vectors. And for the eigenvalue 3, we have an eigenspace spanned by 1 vector.